Dear students, we will discuss about the second type of selective assembly in this session. Let us find the solution of the problem shown here. A clearance of 0.03 plus or minus 0.1 is to be maintained between a piston and cylinder assembly. Cylinders are machined to dia 75H8 tolerance, while pistons are finished by lapping with an IT grade of 4. Use the principles of selective assembly to achieve the required clearance. Find the group limits for cylinders and pistons. We need to maintain a clearance of 0.03 plus or minus 0.1 between the pistons and cylinders. The cylinders are manufactured to dia 75H8, while the pistons are finished by lapping with an IT grade of 4. If you look at the IT grade for the hole is 8. If you look at the IT grade for the shaft, it is 4. So the tolerance value for IT grade 8 will be more than that of 4. So if you look at the characteristics of the type 2 selective assembly, the tolerance of the hole is more than tolerance of the shaft. Here the holes are manufactured to dia 75H8 tolerance. The shafts are manufactured to an IT grade of 4. So naturally, if you look at the table, tolerance table, the tolerance value for the hole will be more than tolerance value for the shaft. The second characteristic is group tolerance of the shaft is equal to total tolerance of the shaft. So these are the two characteristics of second type of selective assembly. So we need to manufacture cylinders, then we need to manufacture pistons, then corresponding group of cylinders and pistons are to be assembled together. If you take the second group of cylinder, it has to be assembled with the second group of piston. So like that, we need to assemble the corresponding groups of cylinders and pistons. So we need to find out the group limit of the cylinders, F1, F2, F3, F4, F5 and so on. Similarly, we need to find out the group limits of the pistons, M1, M2, M3, M4, M5, M6, so on. So this is the graphical representation of the problem. So GH is the group tolerance of the hole, TH is the total tolerance of the hole. The group tolerance as well as total tolerance of the shaft are same, GS equal to TS. So it is shown that the cylinders are manufactured to dia 75H8. The lower limit of the cylinder, if you look at the data book, it comes to 75.000 mm. The upper limit of the cylinders is 75.046. So suppose you want to manufacture 1000 sets of piston cylinder assembly, then we have to have 1000 number of cylinders kept ready. Similarly, we should have 1000 number of pistons kept ready for assembly. On manufacturing the 1000 number of cylinders within a tolerance of 75H8, then we have to group the cylinders according to the sizes. We have to after manufacturing 1000 cylinders, we have to measure each and every cylinder according to the size. It has to be grouped. Then we have to arrive at the group limits of each group of pistons. Only on arriving at the group limits of each sets of piston, we have to start manufacturing the pistons. So this is the main difference between type 1, type 2. In type 1, okay, that is what we have discussed in the last session. We are manufacturing 1000 number of holes, 1000 number of shafts. After manufacturing 1000 number of holes, 1000 number of shaft, we have to measure each and every hole, each and every shaft. Then according to the size, it has to be grouped. Okay, 1, 2, 3 like that. Similarly, according to the size of each piston, it has to be grouped. Corresponding group of cylinders, corresponding group of hole and shaft has to be assembled. Group 2 of hole can be assembled with group B of shaft. So under type 1 selective assembly, we start grouping the holes and shafts after manufacturing the required number of holes and shafts. Under type 2 selective assembly, what we are discussing now, only on knowing the group limits of each group of piston, we can be able to manufacture according to the required sizes. So we cannot manufacture and group under type 2. We have to know the group limit for each group of piston. According to the group limits only, we have to manufacture set of piston for group A, set of piston group B, set of group C piston, set of group D piston. So this is the main difference between type 1 and type 2 selective assembly. Let us solve this problem. The cylinders are to be manufactured to a tolerance of 75 H8 by referring to the data book. The lower limit is found as 75.000 and the upper limit is found as 75.046. So the tolerance of the hole is 0.046. As a second step, we have to satisfy this equation. 2K is equal to GH plus GS. So what is the value of K? In the problem, it is mentioned that a clearance of 0.03 plus or minus 0.1 is to be maintained. So the fit requirement C is equal to C bar plus or minus K. So we need to maintain a mean clearance of 0.03 plus or minus 0.1 between the piston cylinder assembly. So C bar value is 0.03, K value is 0.01. We can substitute K value as 0.01 in this equation. Even then, we are left with two more unknowns. So we have to know any one of these two unknowns. GS value can be found from the data book. So the GS value is nothing but the group tolerance of the shaft. By referring to the data book, the nominal size of the pistons is 75. So for a size of 75, for an IT grade of 4, the tolerance is 0.008 or 8 micron. So the pistons are having a nominal size of 75 and the pistons are finished with an IT grade of 4. So referring to the corresponding column, it is arrived as 8 micron. So GS value is 8 micron, 0.008 mm. So substituting in this equation 2K equal to GH plus GS, I get the value of GH as 0.012. Once I know the value of GH, I can start grouping the holes. The basic size or F1 is the lower limit of first group of cylinders. So F1 value is the basic size of the cylinder, which is nothing but 75. F2 value is B plus GH. The GH values arrived as 0.012. So 75 plus 0.012, you get 75.012. F3 is B plus 2 GH. It is 75.024. F4 is B plus 3 gauge, 75.036. F5 is B plus 4G gauge, 75.048. As per the formula, it comes to 75.048. But if you look at the tolerance for the 75H8, the lower limit is 000, upper limit is 0.046. In that case, we cannot have any cylinder bigger than 75.046. Even though you are getting a size of 75.048 by formula, we cannot have any cylinder bigger than 75.046. So this is truncated to 75.046. So the grouping of the holes has been done. It is written on the figure. 75 is the F1 value, 75.012 is the F2 value, 75.024 is the F3 value, 75.036 and 75.046 are the other values. So grouping of cylinders has been completed. Now we have to find the group limit for piston M1, M2, M3, M4. These are the lower value of group limit for each group of piston A, B, C, D. To find out the M1 value, I want to draw a dimensional chain to get the value of M1 with the help of F1. Now starting from F1, I want to make a dimensional chain to get M1 value. From F1, if the tolerance chain or the dimensional chain moves upward, I take a positive convention. If the dimensional chain is moving downward, I take a negative convention. So from F1, I want to get M1. So M1 is equal to F1 plus I move to the mean of the first group of cylinder, that is nothing but half of G gauge. So F1 plus half of G gauge. Then from here I move to the mean of the first group of piston. So this is nothing but C bar. Then from there I move to the M1, which is nothing but half of the GS. Half of GS. So let me show the loop again. F1 plus half of G gauge minus C bar minus half of GS. So that is what I have written. M1 values arrived from this dimensional chain. F1 plus half of G gauge minus C bar minus half of GS. So it is rewritten as F1 minus C bar plus half of G gauge minus GS. So this formula I am going to use for finding the M1 value with the help of F1 value. So grouping of shafts is done as a next step. M1 is equal to F1 minus C bar plus half of G gauge minus GS. Substituting the value, I get the M1 as 72.972. M2 is F2 minus C bar plus half of G gauge minus GS. It is arrived as 78.984. M3 is F3 minus C bar plus half of G gauge minus GS. The value is 75.996. M4 is F4 minus C bar plus half of G gauge minus GS. The value is 76.008. Now M1 value, M2 value, M3 value, M4 value are written on this figure. Now how to get the upper limit of each group of pistons? Once you know the lower limit, add GS value to the lower limit, you get the upper limit. So 74.972 is the lower limit of first group of piston. You add 8 micron or 0.008, you get 74.980 as the upper limit of first group of piston. Similarly, you add 0.008 with 74.984, you get 75.992. So like that, the upper limit of each group of pistons is found just by adding GS value with the lower limit of corresponding group of pistons. So I have shown the group limits for the pistons. I have shown the group limits for the cylinders. So once the group limits are known, we can start manufacturing the pistons according to the arrived value of sizes. Suppose you want to manufacture 1000 number of assemblies of cylinder and piston, we should manufacture 1000 number of cylinders, we should manufacture 1000 number of pistons. But how many number of piston you have to make under group A, how many number of group B piston you have to make, how many number of group C you have to make, how many number of group T pistons you have to make, it is not equally distributed. Suppose 1000 number of assemblies to be made, then we cannot say that 250 number of piston under group A you have to manufacture 250B, 250C, like that you cannot do it. So the cylinders are normally distributed. The cylinders are normally distributed. So if you look at the cylinders, the normal distribution is expected when the cylinders are manufactured. In that case, if you manufacture the cylinders, 1000 number of cylinder to a size of 75H8, more number of cylinder will have a size close to the mean value. Very few cylinders will have a size close to the lower value of 75. Similarly, very few cylinders have a size close to the upper value of 75.046. So this area under the normal curve will be helpful in finding how many number of piston you have to manufacture under group A. So this area you have to find out, the area under the normal curve between this limit and this limit. So that area is useful to know how many number of group A piston has to be manufactured. Similarly, this area between F2 and F3 is useful to find, know how many number of group B piston have to be manufactured. So naturally, the group P and group C pistons has to be manufactured to a more number compared to group A and group D, going by the area under the normal curve. Once the group limits for cylinders and pistons are arrived, we can cross check with any one group of piston and corresponding group of cylinder. So let us take the group 2 of cylinders assembling with group P of pistons. On assembling group 2 of cylinders with group B of pistons, what is the maximum clearance you get? So group 2 of cylinders has a maximum size of 75.024. Group B of piston has a minimum size of 75.984. So the maximum clearance is the maximum size of the hole minus minimum size of the shaft. So it is 0.4. The minimum clearance is arrived when you assemble a lowest size of the hole under a corresponding group with the highest size of the shaft under the same group. So it is 70.012 minus 74.992, you get 0.02. So the maximum clearance is 0.04, minimum clearance is 0.02 when you assemble group 2 of cylinder with group B of piston. So the mean clearance is found by adding these two divided by 2. You are getting 0.03. From the 0.03, the upper value is varying by plus 0.1. From the 0.03, the lower value is varying by minus 0.1. So plus or minus 0.1 is the variation about the mean clearance of 0.03. So by assembling group 2 of cylinders with group B of pistons, we find that the clearance arrived is 0.03 plus or minus 0.1, which is satisfying our requirement. So we need to maintain a clearance of 0.03 plus or minus 0.1 between the assembly of pistons and cylinders. So that has been satisfied.